Welcome to this session of Shadow the Scientist. My name is Jamaica Marshall, and I am your session host and the Shadow the Scientist Programs Manager. We have the privilege of shadowing members of the Gemini South science team this evening, Carlene Silva, who is the operator for tonight at Gemini South, and James Turner, who's in the observer's seat this evening at Gemini South, with special guest here at Gemini North, where I am in Hilo, Hawaii, Brian Lameau and Emanuele Farina, who will be joining us just a little bit later. Brian and Emma are members of the Gemini North science team. The Shadow the Scientist initiative is brought to you by an amazing team at the University of California, Santa Cruz, and we are funded through a generous grant by the Heisen Simons Foundation. The International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located on two of the best observing sites on the planet. The Gemini North Telescope is located here on Hawaii's Mauna Kea as part of the international community of observatories built to take advantage of the superb atmospheric conditions on this long dormant volcano. The Gemini South Telescope, where Carlene and James are, and we are shadowing them running the Gemini South Telescope, is actually located on Cerro Pachón in the Chilean Andes, where very dry air and negligible cloud cover make this another prime telescope location. Now, by incorporating technologies such as laser guide star adaptive optics and multi-object spectroscopy, astronomers in the Gemini partnership are able to explore the universe in unprecedented depth and detail. And now we are so excited to welcome all of you students to Shadow the Scientist and to this session with Gemini North and Gemini South. Now we're going to be shadowing Carlene and James at Gemini South with, again, support from Brian Lameau and Emanuele Farina. So let's go ahead and start with Carlene, who is already on sky here in Chile. Carlene, welcome.
Thank you, Jamaica, for the introduction. Hello, everyone. I'm Carlene Silva, here and there. We are, now it's 2010. The sunset was around, let me check here, was around 1840. And during the twilight, we did some calibrations, and we slew to the first target of the night already. The conditions tonight are good. Let's see if I can share with you the environment monitor that we use to assess the conditions on the mountain, because we run the observations from the base facility in La Serena. Okay, I just shared it. Hope you all can see it. Here,
yeah, we can see it fine. Yep.
Yeah, I have several ones. I put the environment.
Yeah, there you
go. Okay, here. So here are the conditions on the mountain. We have low humidity, temperature, and low dew point, wind speed is low. So you see all these red marks here, they are limits. If the values are above that, we cannot open. So as a telescope operator, I am responsible for the safety and to make sure it is safe to open. So we have very good conditions tonight. Let's see the... So here the sky is clear. So we can see there are no clouds. And this is the all sky camera. So this is Gemini. This is the Milky Way. And as we see, there are no clouds. This thing is just a reflection. It's an artifact on the camera. So we have good conditions, and we are able to observe tonight. Sorry. Okay, so the first thing we did when we start the night was to select the first. We moved to the first target of the night. I could show you how I did. Let's see. Here. So these are all the windows I have to control the telescope. And here is where I selected the first target.
Carlene, might it be helpful to explain to people like your role and James's role and like how those two interact? And so when you start to pick a target and move to a target, like how does that process work?
Sure, thank you. Thank you for putting me back in the loop. So we observe in pairs because James is in charge of selecting of. So we have a daily plan for observations here, and it's called Q. So we have several options to observe, and according to the conditions, if conditions are good, we follow one of the plans. And then James is responsible for choosing the programs, selecting what we are going to observe, and he's going to do all the measurements with the instrument. And on the other side, tonight I'm going to be in charge of the telescope, its movement, and if there are any problems, also troubleshooting the problems and make sure we can do the observations. So the first thing, he selected the first target, and then I moved the telescope, set up the guiding for the telescope. So we need a star to make the telescope stay pointing to the same position all the time. And then once we are doing that, then James he do the observations. He carries out the observations.
Carlene, maybe you could show a TSD. That might be helpful, like just to kind of get oriented on what the telescope looks like and like where the instruments are. Yeah, perfect.
Yeah, so here we have so this is a schematic of the telescope here. So that in orange here is the position we are observing. So the telescope is pointing here. This black is the opening of the shutter. And then there are two lateral openings here. So they are all open. And here's a schematic of the telescope. So here's the primary mirror. The secondary mirror is here, in the top. And this white trace is the light path. So it enters from here, and then reflects in the secondary, and then comes through that part here. And then there is a tertiary mirror here that sends the light to the instrument. And here are the options of the instrument. So we have five, the light can go to the 5 different options here. And here we had some basic the position of the telescope, yeah, here where the telescope is pointing, the local time, the sidereal time. So yeah, so basically here. And then once the light goes to the instrument, then we have another, we can see another. So here is inside the instrument. So the light continues. So if we look here, you see this, the light is going to an instrument, the number 3, it's called GMOS. And inside GMOS, the light continues. Then it goes to a slit of 1 arcsecond here. And then it goes to a grating with 480 bits. And then the detector where we take the image, save it. So we are here, we have the slit and the grating, and that's where we disperse the light to get the spectrum. So we are doing spectroscopy now. Yeah. And what we could show you next is the image we took.
So, Carlene, you guys have how many instruments on tonight? You have Flamingos 2, you have GMOS, you have Ghost, and I guess if you wanted to, you could use Zorro, right? There's
yeah, we have F2 Ghost and GMOS. So GMOS can do imaging and spectroscopy, and then Ghost do only spectroscopy with very high resolution. And then we have Flamingos that does imaging and spectroscopy, but on infrared.
Infrared, yeah.
The GMOS also in the optical.
Do you think all the students are familiar with the difference between imaging and spectroscopy? Is this part of the lab class they've already taken? So I think you mentioned that they have taken like spectra of elemental lines before. So they have a kind of idea of what spectroscopy is. Is that right?
Let's see.
So right now we're using GMOS in spectroscopic mode. I guess you just showed the instrument status display, and you showed that there was a dispersive grating in the optical path. And so that grating was dispersing the light, the white light, from a target source into its constituent colors. And so it was very similar to what the students have done in the classroom with an elemental lamp, but where you take hydrogen or helium, you throw several thousand volts of electricity through it, it gets excited, and then it emits certain wavelengths. And so the idea is here, I think, probably this is, well, it looks like a very faint source. So let's assume it's extragalactic. So it's from something from another galaxy, and we're placing a slit on it, throwing that light through a dispersive element, making a rainbow, and looking for emission or absorption from different elements, hydrogen, a lot of times hydrogen, oxygen, nitrogen, carbon. And so you're showing right now on the screen, you're sharing a image because you have to pick the image first, right?
Yeah, here is the first image we took from this. from an object here. So it is this very faint one, and we want to take a spectra of that one here.
How long of an exposure time was that image there?
This one, so that one was very. So how much?
The spectrum is 15 minutes.
Yeah, and the acquisition?
Oh, the acquisition, well, I put it to 2 minutes through the
2
slit.
minutes. Okay, so it's 2
2
minutes.
Oh, okay, all right. So, but this is the 2x2 frame here. This
Yes.
Is the, yeah. So this probably like what, 20 seconds or 30 seconds, something like that. But a relatively short time. We don't normally do more than 2 minutes, right, for an acquisition. So this is somewhere between that. Sorry,
I just put it to that. It was very faint through the slit, so I increased it from 30 seconds.
Okay, so the
Okay.
first one was 2 seconds, and then we could use 2 minutes in the tourism. But that one we are seeing right now, it was 30 seconds.
30 seconds. Okay.
And this is so we select this one. I select it twice, so I need to select it once. And then this is an image of the slit. It's very loose. And then we calculate offsets in order to align very well the target, the slit. And then in the so here's the start.
Yeah,
Very
sure,
faint.
got that.
What James said, it was too faint, so he increased the exposure time to 2 minutes. And then we took another one. And it was a little bit better.
There's a noise.
Sorry?
Oh, there was a noise like the guiding.
Sorry?
There was a popping noise like the guiding.
Yeah, but no, that's fine.
Yeah, I think that was
This
just
noise.
back pretending to do something. Yeah.
Okay. So then. Okay.
I'm not used to hearing from that side. When I'm looking.
Yeah, that's the slit again. Well, it's trying to use the slit again, but we can see the stars there.
So it looks like you're getting, we can't actually see your cursor. It's weird. We can't see your cursor in the VNC, but you were going over the target right there and you were getting like 800 counts or something like that.
Yeah.
So in a 2 minute exposure, if you just spin this up, all white light, you're getting like, let's say 800 photons. And so now the observation to disperse the light, it's 15-minute exposures, James? Ciao.
Yeah.
Yes, there's sense exposure for 15 minutes. And then we have some calibration.
Yeah. So then we guarantee that we have a star in the slit, and then we started the science. We see something like this. It's the sequence we have to observe. So we took an exposure of 900 seconds. So we took 1, 2, 3. We are taking the third one now, and then the fourth. And here's the central wavelength we are observing. So we are observing 580 nanometers in the visible. And we are doing a small offset of 20 nanometers just to have it is very close, but just slightly offset in wavelength. And here in the middle are the calibrations. So, and I can show you, well, let's take a look in those things. So here, the first one is the image number 27. So we are going to see that little dot just dispersed in one direction.
Carlene, we can only see the GAC screen. Are you showing a different screen right now? There we go.
That's the, yeah, we are running, okay, let me, okay. So look, that's the raw data we got.
Yeah, you can see the target, but it's very faint in the middle.
Yeah, the target's so faint, but we can see it's that little line here. So we have vertical lines. Those vertical lines are skylines. And then we have the horizontal lines. Those are the spectra of the stars. So this is a bright star that is also in this slit. You can see very clearly here. And then the target is actually that very faint thing. So, but there is no problem because when we are taking 4 of them and we are going to sum them up to be able to see better. And also this data here, this is the raw data. So you see all these tiny little lines all over here, they are cosmic rays. So the image has 10 seconds and that 10 minutes, and during this 10 minutes is all the cosmic rays that are impacting the detector is also giving traces here. So we need to work in that image to get a processed image and take all these imperfections. And you see also there are different, so you see there are different sections that are with different colors, so darker and brighter. So those are difference between the different CCDs of there is an array of CCDs there with different amplifiers, and then it results in different levels here. So we correct all of that to get the processes pretty much after to do the analysis. But this is the raw data we get. And then we can check also we also take we call calibration, but it's actually very similar to take a spectra of a lamp, like hydrogen lamp, but we take a spectra of a copper lamp. And that one is this one here.
If maybe you could bring up segplot because the dynamic range is better on segplot. The scaling is usually better.
Okay.
And then you could just like step through. I can also do it on my screen if you don't have it handy. But yeah, you can just step through to like the flats and arcs.
Yeah. This is a more advanced tool. Let's see, 27. Yeah. So this is the same spectrum. And what Brian said, this one kind of correct that difference in the CCDs. So the target is the very faint one here. And then there is all the cosmic rays. So the next one is another repetition.
Yeah, but this one's actually moved, right? So this is the slit knotting, right? So it's moved about 15 arc seconds along the slit's major axis, and that's to get rid of some of the artifacts there. So if you have artifacts in a particular region of the detector, if you have particular artifacts in some region, by moving the telescopes such that the trace appears in different locations and different exposures. The same thing also for your wavelength movements. So you mentioned earlier, Carlene, that the central wavelength is shifted. And so by moving both in x-axis and y-axis, the x-axis being the central wavelength shift, the y-axis being the telescope nods, then you can mitigate or reduce all these artifacts that are on the detector. These white lines that are sitting in the middle of the detector, those are physical gaps between the chips. And by moving the central wavelength, then you're averaging over those gaps.
Yeah, here I'm showing you another calibration. This is we call flat. It's just we take an image of the we illuminate everything the same. We have a very flat light, and we take an image to see how the different parts of the detector react. So you see there is this white thing here is with what we call the CCD gap, because there is 3 CCDs, and this is the small separation between them. And we also can see that there are regions that are more sensitive to light, so they look like brighter, and then some parts that are darker. And we can correct that. And then we see a black line here. We also correct using this frame. And then the next one here. This is the spectra of the lamp. So we have a copper lamp, copper argon lamp, and we have several lines here. And we use a catalog of those lines that we are identified in the lab, and we can know exactly which line are and the wavelength. And this is going to give the information of the color, because you see everything here is black and white. But we are talking about the spectra that's showing different, that should be showing a rainbow to us. And the information of what is green, what's red, whatever, or blue, it is in the position of those lines here. And then we took another one, and then another flat. This is for the frequency 600 nanometers. So we repeat because it's going to change a little bit. And this is the third spectrum here. And then those lines here, they look like the lines of the lamp that we saw, but those lines are from the sky, because the sky also is emitting in specific lines, and we also can get them here. And if you know one of them, a specific skyline, you can also use that to determine the colors of the spectrum. Yeah. And I think that's a reason of what we did so far.
Are you, Carlene, thanks for showing all that. Are you guys about to transition to a new target, or you have a little bit more time?
Yes, in 8 minutes, we are going to change to another type.
8 minutes. Okay, cool. Okay, why don't we take this time? So the next target is going to be Ghost. Is that right?
Yeah, it's a little more than 10 minutes, I think.
Okay.
And I want to ask Carlene a couple of questions about that, because it's my second time doing Ghost.
Okay, sounds good. Maybe we can then transition over to our special guest.
Special.
Who can introduce the Ghost instrument, and then the science, some of the science that can be done with the Ghost instrument. So this is Emma.
Mr. Special for you.
Special Emma, and he's gonna show us some results.
Hi everyone. I actually never observed with ghosts, so I'm 2 steps behind James on this. I know even less on the operation part. But I try to play with Ghost. Ghost is actually one of the newest instruments at Gemini. It has has been smartly built. It's a spectrograph, but it's not a spectrograph like GMOS. GMOS that you see this a slit spectrograph mainly, or what you just see was a slit spectrograph. It means you put a little aperture on the sky and you collect the lights only coming from this aperture. While GOST has been built in a, I will not say smarter, but it's like more efficient way for do some specific experiments. So instead of having a slit, you have a bundle of fiber optics, and each of these fibers collect the lights from the sky, and they're all attached together. So basically, you don't lose any lights coming out from it. So if in your best image of a star you can imagine is that it's something like circular, and all the fibers are put together to make a circular shape. So you actually collect all the lights that come from the star without losing anything, or basically anything. It's in good seeing condition. So when the sky is really good, the shape is really like a point source, you put your bundle of fiber on that and you're all good. That is helpful because when you have a slit, you have something that is rectangular. When you have a source is circular, so being circular is more optimal. This comes to a price of something that you don't have. When you put a slit on, you have both the source and the sky on the detector. And that's what was shown before, that you have your source in the middle and you have all the skylines. And when you want to subtract skylines, that comes for free because the detector has them. You can just model them, say, okay, I know how to behave under the source, you subtract them. But if you all the source,
What's the typical contrast between the skylines and a source?
it depends on what you're looking at. So when you look for like the brightest stars in the universe, or in our Milky Way, actually, is actually typically the source is brighter than the stars. But the source is brighter on the skylines. But if you do like me and Brian, that likes to go as faint as you can, that's why we like 8-meter telescope, because you can push it to their limits. Then when some of the lines, like several 10,000 times fainter, something like that in some region.
Yeah,
So
so you're dealing with the contrast of 10 to 100,000 times just right off the bat.
Yes.
So the skylines and the background sky, right? Just the normal background sky.
And so it's suboptimal, but the GOST builder were actually smart enough that said, oh, you know what? Instead of having one, can we have two of these fiber bundles that can observe the sky and the source at the same time? So basically what you do, well, you can directly subtract this from one. You put one bundle on the source that you're interested in, and the other bundle on the sky, and you do source minus sky directly. And so you have basically a perfectly sky subtracted spectrum. But then they were even smarter than that, because they say, okay, let's say there are some people that are interested, instead of me and Brian, that will go to a faint object, we want to get something that is like bright. And we want to observe two targets at the same time, because they're close enough that we can put the two fibers on the two sources. So we are like 2 times more efficient. And if you can imagine that telescope time costs between $1 to $2 per second, if you have a factor of 2 faster, your 1 hour observation, instead of costing $3,600, costs $1,800, which is substantial. If you go to the supermarket, there is a 50% discount, you consider. But then you don't have the sky, so they build another little fiber that can go in a position just below one of the two bundles. And then at that point, you're able to subtract the sky. And that's in the skies is like, given that for bright sources, actually the skies get less relevant. Having just a coarse measurement of the sky is enough, and you can just subtract it. And so the instrument itself is really beautiful. You're showing this?
Yeah.
Yes, sir. So in this case, you can see that they put the two IFU, so the two fiber bundles are located in 2 positions, one in there, and below, I think, somewhere below one of the two, there should be a 1 fiber that is used for the sky. I don't remember which one.
Yeah.
I think under the 1, I'm not sure.
Yeah, IFU 1 is at the top.
Yeah. So of course, given that there are like 2 arms that moving the bundles, there are some limitations, so you cannot go out from this shaded area when you put 2 sources. And so you have a little bit of limitation, but actually like it's super flexible, super nice. It's a great instrument. So GOST actually works in what it does is actually super high resolution spectroscopy. That means that it's a resolution that GMOS cannot reach, and you have moving sources. So.
Yeah, so this is just a stepping program. So it's stepping to different stars within this.
Yeah.
So you see the IFUs just moving to these different stellar sources.
I was confused for a minute.
Yes.
Okay.
That's real. That was intended behavior.
Yeah, but that's beautiful. No, you get 2 spectra at a time that comes for free. So the spectral resolution is what is important for this instrument, and the flash calibration is actually spectral. So the spectral resolution, it tells you what is the smallest feature you can resolve in terms of like broadening of the line that you can observe. So we use a weird measurement of that we call R, that is lambda over delta lambda. It means what is the size in delta lambda of the feature you can observe at which wavelengths. That sounds terrible, but when you want to think about something that is not in angstrom or in nanometer or something like that, you want to think about something that is kilometer per second. And so that gets super easy because you take the speed of light, you divide it by this magical number R, and then you have the measurement in kilometer per second. So assuming that the speed of light is 300,000 kilometers per second, given or take few hundred kilometers per second. If you have a resolution of 1,000, the smallest things you can observe is 300 kilometers. That's why we use that number, which makes super nice. So typical GMOS observation go up to a resolution of 1,000, something like that. You can go a little better at that, but it's rule of thumb is like you can take it in the middle is 1,000. And what we're talking with GOS, we are talking of 45,000 or 75,000, if I remember.
Yeah,
I never use
80,000.
I never
Tigers
use that.
too is 45,000.
I never use that one. No, there are 2 modes. There is a low resolution and there is.
Yeah.
So it's like basically to have in mind is like tens of thousands better than that. And so when you start to be able to resolve things that are as wide as like few tens of kilometers per second, and then what things get interesting. And the other important thing is the flash calibration. So it's with slit, you only take a fraction of the lights that it goes in the slit.
Right. Sorry, just on that point. So 10 kilometers per second still seems pretty fast. Is that fast in cosmological terms?
Yes.
It is still fast. Yeah.
It really depends on what you're looking for. So there are people that, when I talk with people that work on solar system, on our sun, when you say, oh, your resolution of 10, they say, oh, of 10 kilometers per second, they say, oh, you mean centimeter per second, because they can split the lights in like infinite little beams, because the sun is turned out to be pretty bright with respect to any star you can imagine. So it depends on what the science you're doing. For what I'm interested in, you can imagine that a typical velocity dispersion of a galaxy is between 100 and 200 kilometers per second.
Yeah. So we're traveling around
200 kilometers.
Yeah, 220 kilometers per second.
So
around the Milky Way.
Yeah, as ourselves is going to that speed. So if you want to measure how fast is a galaxy, that's more or less what you want to do. And if you have 10 kilometers per second, you can split your distribution of velocity in like 20 resolution beams. That means you can do a measurement in 20 different parts to see how the things changes. I don't remember what it was.
Then you were doing flux calibration.
The flux calibration actually is the really tricky part for this kind of observation.
Can you explain what flux calibration?
Okay. So when you take a classical GMOS exposure with the slit on, you can imagine like your star is like a certain size, and then you put a slit on it, and only a fraction of this light goes into the slit, and you measure how much flux goes in that light, and you have your measurement. And then you go to a star that you know perfectly what the flux is. We make exactly the same experiment with the same wavelength, the same configuration, the same slit and everything. And that tells you the ratio between the known spectrum, the model spectrum of the star versus what you observe is what we call the flux calibration. So you take the ratio between the two, and then you multiply that to all your measurement, and that's give you for every single wavelength what is the real flux corresponding to that. But there is a lot of uncertainties in this process. One above all is what is called slit losses. That is, with no surprise, how much light you lose because of the slit. So that's what I was saying before. Now your slit is rectangular, your source is round, and so the edges of the source are going to be lost. But if you have a bundle of fiber that match the shape of the source, what you actually have, you don't have slit losses. And so you have 100% of the light entering your system. And so once you have 100% of the light entering the system, you don't have to have this extra term of correction, it's called, due to the slit losses. And these are the two things that actually GOES does magnificently: resolve small features and be super perfectly calibrated spectrum in flux.
Emma, so you are the contact scientist for GHOST. What does that mean?
Oh, that's an interesting question.
Uh-oh.
So
Here we've got a few left.
Okay, we are moving in 1 minute, more or less.
Oh.
getting
Please
there,
continue.
and I want to stress one thing that is not appreciated enough. James is switching instrument, and nobody will actually notice it if I don't say that, because Gemini is extremely fast in doing this kind of things.
Yeah, seamless.
Yes, thank you.
Mm-hmm.
So you're moving from GMOS to GOES, and there are some telescopes that require an entire day of day crew work to actually switch from instrument to another.
Mm-hmm.
And Gemini has compact design with all the instruments that are attached to the bottom of the telescope.
Carlene, can I grab the screen share for just 1 second? Oh, you got the, okay, never mind. You got the TST up. That's exactly what I was going to show. Yep, please.
And so you see on what Brian is showing now, on the bottom right of this yellowish color.
G10619, please.
Yes.
In the bottom right, you see that there is the light path of the telescope. So you see that now something is blinking and the mirror turned out to be red, and you see that there is GMOS written, and I don't see GOES on the bottom of things. So basically, instead of having instrument that being replaced on the telescope, we have a mirror that shifts the lights between different instruments. And actually, given that GMOS was in port 3, that is on one of the side port, that means it's attached on the side of the telescope, while GOES, the lights go straight down to the hole and is visible from the bottom part. You don't need to have a mirror there. So instead of moving the mirror, you actually fully remove the mirror. But that's while I was talking, the instrument exchange happened. So it was actually a matter of seconds, which is unique, I think, among 8-meter telescopes.
And we can see it on the left. Is that the dome turning?
Yeah, so the black portion there, the two flanking black portions are the vent gates, which Carlene mentioned are all the way open, these lateral vent gates. And then the diagonal black region there is the shutter opening, and the dashed circle there, that's the telescope. So the telescope has arrived at the orange, almost arrived at the orange dot, which is the rough location of the target. The dome is now slowing to keep up. But as Emma said, I mean, we're already done with the instrument switch. So this is a big slew. They went basically the entire distance of the sky. But it's so fast that our instrument switch will happen faster than our telescope movement. And our telescope movement is pretty fast. So yeah.
This is that mirror that was here sending the light to GMOS in the number 3. Just remove that, and then the light can go down to GOES. It's here.
Yeah, so you just basically park the tertiary, right? Science fold.
Yeah, the science fold was parked. And then you see here, the light path is green. It's gray because the dome is still not in position. And once it is in position, then it will be white. So indicating that the light is going to GOES.
So
Carly and James, since you guys are going to be a little bit busy now, the acquisition process requires pretty concerted effort on both your parts. Maybe we can talk a little bit of science, and then we can come back and kind of peek over your shoulders every once in a while.
Yeah, I just sent some questions that they are interested if you could review them as well.
Sorry, can you repeat, Carly?
I just sent a list of questions on the chat. If you could just that the students are interested on those questions. I think we talk a little bit about some of them, but just to have the question.
No, I didn't actually get any chat from you, Carlene. You put it in like the full chat, or did it go to particular participant? Was it on the Zoom chat?
No, it wasn't your Google chat.
Google Chat. Yeah, you guys use that a lot more than we do. Sorry. Okay, let me,
I think we are in position now. We have lights, so.
Okay, sounds good. Yeah, okay. So I got them. So I'm just going to put them in our main chat here, so everybody can see them.
Thank you so much, Brian. And while Brian's doing that, Emma, could you talk a little bit about being the support scientist for GHOST?
So we are, well, everyone here basically is an interface between the dreams of scientists and the reality of operations. So basically the process is that people ask for telescope time. So they write a compelling observing proposal saying, hey, I want to observe for 10 hours this specific target in the sky. Mm-hmm. And everyone in the world does similar things. At the end of the day, there is a panel that ranked for the proposal and got a fraction of this proposal, like roughly 20%, 30% of this proposal get accepted. It means it comes to us. And we are contact scientists. It means that we read this proposal, we provide a first round of suggesting this is feasible, what you're proposing to do, and how can be optimized. And then we start to talk with the user that actually ask, or the scientist that ask for this specific estimation. And so what happens is that the PI, or the principal investigation that asks for the time, starts to prepare the observation, say, okay, I want to observe this target for like 600 seconds every 3 months with some constraint. And then we go through all these observations with all these requirements, and we check if that's are correct, realistic, or can be improved. For instance, there is one limitation that is for GMOS, that technically you can expose for as long as you want, not as long as you want, but you can go you can have exposure that are really long, and there is really few limitation because the sky is fairly faint in the optical, and so there is little risk to arrive to saturation or something like that. But the drawback of that is what was shown before, that GMOS is a fairly thick instrument, so it means you have a lot of cosmic rays. And we turned out that if you observe for much longer than 20 minutes, at the end of the day, your entire image is contaminated by cosmic ray, you can just throw it in the garbage. And so there is why technically you can observe for half an hour or 1 hour with no big deal. We recommend to go well below 20 minutes. And this is a subtlety that maybe not everyone is aware of, but given that we are the expert, or we are supposed to know what the instrument is doing, we can guide that guideline and say, hey, if you want to observe for that long, and maybe it's better to switch in 2 parts. And while the instrument most of the time are well behaved, there is a huge fraction of the time that actually something happening, because they are extremely complicated instrument. Especially if you work in the infrared, you work at cryogenic temperatures, and it means that everything that behaves normally at normal temperature doesn't behave normally at cryogenic. You don't have, I learned something that you cannot put oil and freeze it, because then it will not lubricate anymore, anything. So you have to work like with dry lubrication, and makes everything things. And things shrinks, and you don't know how much they shrink. And
Oh, wow.
Or GMOS, at a certain point, have a glitch on one of the detector, then now it's been fixed. But one of the amplifier was actually like basically dead completely. And so we had a gigantic gap in the detector. And all these things are not known when someone asks for telescope time. And we know at the moment, so we can suggest way to mitigate that, or say, hey, if you really need that part of the spectrum, we probably fix it in a month, and so we can come back with that or something. So that's our role, is to be to make sure that whenever someone asks us, we want to do this science, we make sure that the telescope is the best use to arrive to that level of science. Basically, that's the summary.
Yes, but this is just one role of the many roles that are taken on by staff at the observatory. So, like, for example, Emma and I might be in the chair of the
share
screen.
the ghost screen? Okay.
Yeah. Sorry, which screen?
You see, it's very saturated.
Mhm.
So you
Yeah.
can reduce to 0.1. And you could actually use binning one by one as well.
Okay.
And then you can,
Which screen are you guys on, Carly?
the top, at the bottom left.
Bottom left, bottom right.
Right, sorry.
Bottom right. Yeah, there's I can't remember where you switch between which fibers are visible, but should I start exposing?
Take another single, let's see, because it's very far from.
Some of them, yeah.
Is it applying the corrections? No, so you need to select use correction, yeah, because it's not moving.
Yeah, so what we're looking at right now is the ghost control screen. So basically, as you saw earlier, the light from the telescope is being piped to the ghost instrument now. And these are preliminary images, acquisition images for the target that the program, the principal investigator of the program wants to look at. And so I don't know much about ghost. I know less than Emma does. I have never used it in operations. We don't have an equivalent in the north. And I've never observed it in the south.
Yeah, that's the first time I've seen this image, so it's pretty exciting. I'm on your same boat, so it's fascinating as you are.
Yeah, but I assume what you guys are doing now is just centering up the target and trying not to have it saturate.
Yeah.
Yeah, we did that. So the panel here you should look is that one that has 6 dots. And that's the star moving around. Those are 6 fibers that are keeping the target in position. And you can see that red dots that's jumping over, down and up.
Yeah.
And the science fiber is in the middle of those. So those are the guiding fibers.
Okay.
And then the science is in the middle, but we cannot see it because it's going to the spectrometer.
Mm-hmm. And you guys are integrating right now. So this is the on-instrument wavefront sensor, basically. And you guys are also sending light to the science fiber right now.
Yeah. So we are ready. Could start.
Yeah. So.
Okay, maybe we can show a reduced ghost a spectrum, and then we can go over some of the questions that the students have in the chat. So
It seems a little unstable, but I don't suppose we can really do better.
No, that's for sure. But the saturation is not a problem.
Yeah.
Okay. Emma, do you want to share what this is? Would you mind sharing what this is?
Yep.
You're not doing anything. Let's see, because we need to start. Start taking the image and then we start taking it. So we are ready. Good
I don't need to do anything else. Just
no.
So
And
this is
I can show
redshift.
Yeah, it's okay.
These are redshift 5-ish quasar. So what a quasar is, a supermassive black hole by accident in the sky is eating a lot of gas and dust and stars and everything. And so it turned out that it's emitting a lot of light. And just to have a reference, if you think about one star, that these things are like, so the Milky Way is around 10 to the 11 stars, and these things are brighter than the Milky Way. So it's this total light that come out from a single supermassive black hole is like 1,000 times brighter than the sum of all the stars on the Milky Way.
So 1,100 billion stars,
Yes, equivalent of.
1,100 billion stars.
or
Yes.
100 trillion. Yeah.
It's a complicated number, but just the idea is to give you the reference that these objects are extremely bright. They're brightest than everything you can imagine around you that you can see in the sky with naked eye at the moment. And this is pretty amazing because given that they're so bright, it's actually visible in the entirety of the universe. So even if you go like at the beginning of the universe, you can still detect them and see them.
So
And that,
these ones are like when the universe was like 1 billion years old. So
Yeah, so-
maybe like 10% of its current age
Yes,
or
okay.
less. Yeah.
yeah, 8%. More or less. It's like it's pretty, the universe is around 13 gigayears, and these are like around 1 to 2 gigayears old. So it's a pretty young, pretty beginning of the universe. And one interesting thing, don't only spot where the supermassive black hole are, but you also can see everything that is between the black hole and us. And so when you see on the right side is the continuum, this is actually the shape of the emission of the black hole. And when you look to the left side, the continuum should be the same, but you actually have all the hydrogen clouds, that every single hydrogen cloud that is between us and the quasar create this absorption, what is called the Lyman alpha forest, of like lines that got fully absorbed.
Yeah. So, just to orient on this plot, flux on the left-hand side is basically brightness. It's a unit of brightness, it's a apparent brightness. So what we measure at the telescope, and it's measured in energy units per time per a unit area. So you can just think of it as brightness, and then wavelength on the x-axis, that's just color, basically. It's a numerical way of saying color. So this 6,600 angstroms, that's what the symbol is here. That's what we see is like reddish. The range of human vision goes up to about here. So actually, this part wouldn't be so visible to most humans. We would just see the forest if we could see. And when Emma says like naked eye, this is still like what, 18th magnitude or something like that? Yeah, so this is 12 magnitudes. Let's make the math easy. 12.5 magnitudes fainter than the best human vision. So magnitude system is this really weird system that astronomers use still for some reason. We have a lot of conventions that don't make any sense. But every 2.5 magnitudes is a factor of 10 in brightness. So if you have 12.5, that's 5, so 10 to the 5. So 100,000 times fainter than the human eye can see. And this is bright. This is what, like, this would blow out the detector on our telescope if we just fed it right in. If James took a 2-minute image with GMOS like he did with the last observation, this thing would be like blooming on the detector.
Yeah. Magnitudes are awesome. One magnitude is a factor of is 2 stars that are 1 magnitude different. It look a factor of 2 fainter.
We don't have time to defend the magnitude
Okay.
system here.
Go quickly. Basically, what we are saying, there is hydrogen atoms in the universe. Every hydrogen atom should have an electron. And when this electron got hit by the light of the quasar, it got excited and disappeared, but the energy that you need to excite this electron got absorbed fully. And so you don't see. That's why every single specific wavelength is one photon that got absorbed by an atom in the, like you can imagine that here. It's a cumulative effect. But that's what you're seeing. So, yes. So what we are looking here is basically, you can imagine that every time there is something that it goes, so the blue curve on the top is what the emission should look like if there would be no hydrogen in the universe. And every time you see something that is below the blue curve, it means there was at least 1 atom of hydrogen that are fully absorbed. And there is you can already see from this beautiful spectrum that there is a variety of properties. There are super, super narrow lines, and that's why Gauss is beautiful, because you resolve basically everything. But then exactly at 7,600, you can see that it's something that is slightly bigger and get even more crazy when you go to 7,300. These are gigantic pockets of gas that fully absorb the light at the point that there is no emission happening anymore at this position. So what we're learning from this thing is basically, you can imagine that imprint on this spectrum, there is the entire universe. So the distribution of the entire gas of the entire universe
Along the line.
along the side.
Yeah.
I'm simplifying it.
Yeah.
But on the single line of sight, as Brian correctly corrected me, you have the information of whatever the universe is doing in the entire line of sight.
Yeah. So if you had quasars every single point in the sky, then you'd be able to reconstruct the matter distribution of the entire universe. Unfortunately, I don't know.
There is only 1 million quasar, and until now that is still not enough to do that experiment.
Yeah.
There are 1 million
Turns out it's
quasars
a big ass sky.
that is bright enough, and covering of 1 square second over 4 pi.
Yeah, it's a lot.
It's a lot. You need way more quasars to do that. But specifically for this experiment, that what you can imagine that is, now I'm going a little bit in details, but I think it's fascinating. The distribution of velocity of the gas that you're seeing there
10 to the 14. 10 to the 14.
Yes.
Yeah, 10 to the 14.
quasars.
Yeah.
We are
100 trillion. We're back to 100 trillion.
Okay, there.
Mhm.
10 to the 6, so we are 10 to the 9 short. While Brian does math in his head, you can imagine that for every single pocket of gas you see, if you can measure the distribution of velocity, that's telling you how hot or what the atoms inside this pocket of gas are doing. They're moving a lot, they're moving a little, they're like just on a shield and everything. So it's too complicated. I'll go there.
Yeah.
Thank you. You can imagine that there are different things that contribute to that. But if you imagine that the universe is full of dark matter, dark matter is like a line along streams, and along the stream also the baryonic matter that the matter we can see is tracing each other. So this is, aside of one case, we always see that there is dark matter associated with matter that we can see. So that means they should influence a little bit each other, or the gravity of the dark matter should influence the movement of the baryon. That's the reality of things. So when we did this measurement, by knowing how broad these single lines are, we can infer property of the dark matter that by definition we should not be able to see, but we can see the impact of that. Mm-hmm. So when we have this superb instrument that allow you to do such precise measurement, what you actually are doing is saying, you know what, dark matter, we are testing you. We are seeing where you are, what you're doing, and whatever you were doing in the universe in the past. So that's the entire point of these single objects. And when you start to build a system, you can do statistic, as Brian said, you have one line of sight, but when you start to have like a million line of sight, you can do the experiment a million times, and you can start to find out what are the average property of the universe to cosmic time. And given that there is different dark matter models have different expectation of how the gas should move, or how the dark matter should move, and then how the corresponding visible matter should move, then you can infer those. I think that was my 3 minutes explanation why this pattern is super awesome.
Yeah, so just coming back to what I was saying before is that we all have to...
We are guiding the next target, and we are ready for the acquisition.
Okay.
If you could
yeah.
Go to James's screen for the acquisition.
Yes, of course. Which screen are you doing it on, James? Bottom left?
Yeah.
You can do that.
It's in the finding chart.
And no, we see seg plot.
Oh,
yeah.
Interesting.
So you can see
yeah.
that the light is dispersed in so many beams that you actually need to pack it in one on the top of the other. Otherwise, you will not have enough space on the telescope to actually collect all the lights in one single line. I did that.
Okay, so James is bringing in a finder chart right now.
Yeah, it's on the screen above. It's a kind of a blurry colored finding chart label there. Work out nice.
Okay, there it is. You just have to find the crosshairs, James, in the universe. Then you're good. Right, so there was a quick ghost observation, and now we're back to GMOS, I guess. So Carlene and James are going to go through that process right now. But the actual gacking is going to take place on which screen, James? I can just leave that as a kind of background.
That's it. Just discovered that the keyboard repeat doesn't work if you have numlock on. I didn't remember that. It's super annoying when it happens.
Oh, there it goes. Okay. Okay, so yeah, they're doing an acquisition right now. They're looking for the targets. Basically the same thing that Carlene showed earlier. That shadow that you see there, that's not a real thing in the universe. That is an alien finger, otherwise known as an on-instrument wavefront sensor. So it's a little pick-off mirror. It's like a dentist tool, basically. So it's like this little mirror that goes out, and it's like, hey, and then it gets a little star, and well, probably a pretty big star. And then it collects the light from that star. It disperses the light into four or six different arrays, and it makes sure that the star stays centered in a given location. By virtue of that, we know the difference in the angular distance between that star and the target star, and so you can keep things nice and stable and guiding for very long exposures. So like last time that a target was observed at the beginning of the session, they were on that target for like an hour and a half, and they didn't have to do any tweaking of the telescope during that time. All on instrument wavefront sensor, just keeping things nice and stable throughout the entire time. So going back to what I was saying earlier, we all have different roles. Sometimes I would be in the same role as James, Emma as well, although the equivalent here in the North. Currently, I'm coordinating the queue and running the science operations here. So like if James and Carlene were at Gemini North, I would be passing them plans for the night. And then they would be using those to help guide their decision-making processes.
Brian sounds like he's doing a lot, but actually he's knowing.
Yeah, I'm going to show you guys.
We are close.
I'm going to show you guys that in a second, because it's apropos of one of the questions that you asked. So yeah, we actually canceled the night up here already in the North, or I did. That's right before I came to the session. But one of the things I wanted to highlight is that Emma, being a support astronomer, let's say, for the ghost instrument, or being involved in the ghost instrument in some way, he's also a scientist. That's his I don't know, night job, day job, whatever, side hustle. And so so he would say, hey guys, there's this really, he's talking to his collaborators, of course. Hey, there's this new instrument that's coming online. I know some things about it. It looks pretty cool. What about this idea? And this helps germinate, because Emma he's talking about being the liaison or conduit between the dreams of scientists and the harsh realities of operations, being able to incorporate that and then contextualize that for collaborators and say, hey, this would actually work. This experiment would actually work. Then germinates these types of really wonderful collaborations. So it's not just that we're servicing the community in the sense that they pass ideas here, and then we affect those ideas, but there's a nice feedback process where it comes to us and we propose back to them, and then they propose back to us. And all of science is served by that. And so we have certain expertise that they don't have. They have other expertise that we don't have, and we work together synergistically. So I wanted to get to you guys' questions. I know we're like 15 minutes over the kind of normal cutoff time that we had. So one of the things we just hit on, so there was a question about why was Gemini South built at this location? So let me just, I'm going to stop sharing on the acquisition. Well, I guess this is the exciting part. You guys are, acquiring the target. Yeah. There's the target. It's a lot brighter than before. Different target.
Yeah. And we're back on GMOS, right?
Back on GMOS, yes. This is long slit.
Yes.
Yeah. So it looks like they're nice and acquired. This is just looking at the target through the slit. It looks centered along the minor axis there.
Yeah, that was pretty good, and it's we set it to the parallaxic angle so that the dispersion of the light in different colors goes along the slit instead of across it, and then you don't lose light.
Right. So you tilt the slit, or basically you tilt this Cassegrain rotator in some way to move the slit's orientation on the sky. and there's this angle called the parallactic angle along which the light is dispersed. And if you turn the slit such that it's at that angle, it will collect, there will be no chromatic differences. So if you had to, like, if you're perpendicular to that angle, you'd actually differentially lose blue or red light, depending on how you oriented it, usually blue light, because it's higher energy, so it refracts more. But if you turn it parallel to this angle, then you collect all of that light and you don't, the slit losses that Emma talked about are achromatic, meaning they don't depend on the wavelength, which is really important because a lot of times you're measuring differences in the shape of the continuum. You imagine the spectrum that Emma just showed. If you induce some color gradient there, you may change the scientific results that you get out, and unknowingly, just because you happen to orient the angle in the wrong way. So this is, again, the harsh realities of operations versus the kind of dream world of some of the science. You can throw all the wonderful models that you want at it, but if your data's crap or you don't know what's called systematics, these systematics that are underneath the data, then you can't correct for them, or they enter into your science in a bad way. So let's start with the Gemini South built at this location. So right now it's 3 o'clock in the afternoon in Hawaii. It is not 3 o'clock in the afternoon in Chile. It's 9:15 in the evening. They're observing, we're not. That's not just because we're covered in snow right now. It's because it's daytime right here. So we have now 6 hours difference. Some other times of the year, 7 hours difference between Chile and Hawaii. So a large fraction of the time, one of the two observatories is open. So if something exciting happens somewhere in the universe, chances are that we're going to be open somewhere. We're also in 2 different hemispheres. We're at roughly 20 degrees away from the equator in each direction. So we can see a large swath of the sky, both of us, but Gemini South can see some things at the south pole that we can't, celestial pole, and we can see some things at the north celestial pole that they can't. And so the combination of these two is very effective because you have night in one location, day in the other, the ability to see all the way to the north pole, celestial pole in the north, and then vice versa in the south. Both sites, Cerro Pachón and Mauna Kea, as Jamika mentioned in her introduction, very dry in general, not right now, very dry, and have very nice laminar flow of wind over their location. So turbulence in the atmosphere and on the ground is really important for, you want to minimize that as much as possible to get as much light as possible in your instruments. And so both of these sites have exceptional levels of constant wind going over their sites, and the topography of the land is good to basically destroy any turbulence that's in the lower atmosphere. Those are all good reasons. Another good reason is that it's winter in Chile when it's summer here, and vice versa. So they have spectacular skies right now. So just going back to what they see in Cerro Pachón. Okay, so this is what they're seeing right now. Beautiful. These stars, you can see shooting stars. Everything looks
Magellanic clouds.
The Magellanic clouds. Yep. Here's what we see at Gemini North right now. We see fog.
Clouds.
We see clouds. We see ice. We see snow. And so while we've been closed for the better part of a month, and so we're not getting any astronomical photons right now. But Gemini South, on the other hand, it has pretty decent weather, and they're able to observe. So we kind of share programs, we share the queue in some ways, and so we can pass back and forth as necessary on occasion. But yeah, so these are 2 of the best sites in the world, and this is why they were built in these 2 locations. We've covered a lot of these other questions, I think. So I'll just mention quickly the main observing techniques used at Gemini South are very similar to what we use here. It's imaging, so just taking images in different colors in the sky, spectroscopy, whether that's low resolution or high resolution, and speckle imaging, which is a technique used to take very quick images of the sky for very bright targets. Both the North and the South have this capability. And the idea is to average over the fluctuations in the atmosphere to go faster, basically take images faster than those fluctuations. And through a mathematical technique, you can reconstruct the true size and shape of sources on the sky. So you can basically get down to what's called the diffraction limit of the telescope. So think of James Webb or the Hubble Space Telescope. Basically can get to the same resolution, spatial resolution.
Well, I correct you there. Given that we have a
Yeah.
bigger mirror and the diffraction limit is proportional to the size of the mirror, we actually, in the best ever condition, we are better than HST and JWST.
Yeah.
Which is impressive.
Yeah. And it's also true in like very like far infrared for ground-based observations. The atmosphere is not so turbulent, and Gemini is infrared optimized, so we can observe at like 5 microns. And same thing, we can get down to on very good nights, we get to the diffraction limit on Mauna Kea, and that beats James Webb. So I've been a part of observations that have beat James Webb before, and that's even without any special mathematical techniques.
But we just need bright targets, because the problem that the atmosphere getting brighter and brighter, so your background gets brighter. So what I'm saying is not that James Webb we should not have built it. It was an expensive and useful instrument. But in terms of spatial resolution in the sky, our 8-meter telescope on the ground for specific experiment is better than the James Webb.
Yeah. But yeah, this guy is annoying for astronomy. It's good for other reasons. Atmosphere is good for other reasons. I'm generally pro atmosphere, but there's just every once in a while that's can get in the way. And then so we talked about how spectroscopy is used to study various types of astronomical objects. The Doppler effect is something that we haven't named, but Emma gave another name for it, which is called redshift. Another name for it is velocity, basically. So when Emma was talking about hundreds or thousands or tens of kilometers per second, objects traveling at the speed will cause shifts in the light, and we'll measure that in spectroscopy. So if you see a certain wavelength versus another wavelength, then you can tell something about the kinematics, the motion of those sources. And as a base, like I work on galaxy surveys, so looking at tons of galaxies, trying to understand the distribution of those galaxies on the sky. And so at a base level, when we measure a spectrum, we match that up to a lab line. So if we're looking for hydrogen, we see an emission of hydrogen in a galaxy. We say, what's that in the lab? Okay, that's on Earth, it's this thing, or in a vacuum, it's this thing, this wavelength. And we basically divide in those quantities to one another. So what we measured it, what we know it is to be in the lab, we subtract 1 from that quantity, and that tells us the distance of that source away from us, because the universe is expanding. So that's like the base level Doppler effect. You can also use this for detecting exoplanets, so planets around other stars. As the star wobbles around the mass very center of the system, you can tell that there's planets tugging on it. You can use it for foreground sources, so looking at gas clouds, the actual movement. You can look at the rotation of galaxies. So this is another way that you can look at dark matter. I was talking about the rotation curve of the Milky Way or other galaxies, a couple hundred kilometers per second. If you keep taking spectroscopy further and further out, what you see is that rotation doesn't really decline in terms of its overall magnitude. So the velocity is basically constant. And so that tells you that there's hidden mass that you can't see. This is one of the first indications that baryonic matter, or matter that we can see, is not the only matter in the universe. So these are all Doppler effect kind of things. It's basically just light and movement. And then you throw models at the problem eventually, which is what Emma was showing. We've shown plenty of examples of measurements that have been taken Gemini South, even ones that we're taking right now, which is awesome. Maybe James, Carlene, if just to round us out for the session, the last question is about how you guys like prepare for an observing.
Can I
night?
interject that 1 second?
Yeah.
I think the main thing is coffee. And you see, James, I don't know if that in front of you is coffee or tea. But yeah.
It's actually tea. I'm afraid I'm very British in that regard, but yes, something along those
Anything
lines.
that is caffeinated or stimulating enough to keep you awake and super focused for sometimes between 10 and 15 hours. It's useful.
Yeah,
in Hawaii,
I mean, 24-hour shifts is usually what we do on the worst.
Yeah, but Brian goes for light Coke. He's like, you can decide what you go, but
and 3 cups of coffee.
Yes, I never seen a single astronomer just going without drinking a single sip of caffeinated things during a 5-night shift.
No, in Hawaii, people have even been known to drink Mountain Dew out of desperation, I think.
It's sitting in the side of the control room for decades, just beckoning.
But I let you speak something above caffeine.
Yeah, can you guys describe like your kind of normal process?
Get coffee in the beginning, because if I drink coffee over the night, I get stressed and anxious. So can have the opposite effect, because you need to be very patient to stay 10 hours here and doing this deal and doing the same thing over and over and over and paying attention to all the details.
You need acai.
Yeah, but too much energy in the night also not good. Then you start to the problem. When you get a problem, you need to have your mind clear and be patient to solve it.
Yeah, that's
but
true.
If you have too much coffee and you are too excited, then it actually interferes. You don't follow the instructions or don't read things calm enough. Then you make mistakes by being too accelerated. So I just drink 1 coffee, and then if I get sleepy or something like that, I usually just rest the next day. The next day I try to sleep more to be able to be awake without the coffee, because at least for me it doesn't help late.
Yeah, you can lose a lot of time if you're not calm.
Yes. But other than that, most of the preparation for the observations is done by the Q coordinator. In that case, Brian, it's not doing much because they have snow there, but there was a Q coordinator for the south, and that person did all the planning for the observations. And we don't do that. I know that if I come here and whatever condition it is, it doesn't, I don't worry about if the sky will be clear, if conditions are good or not, because I know there will be something to do in any of those conditions. And that's the plan that the astronomer did during the day. I'm going to follow it the best I can and switch in case the conditions change. And of course, if it's too bad, we just close the telescope and wait until, and sometimes it's midnight and conditions aren't changed. We look, that link I sent to you, there is the satellite image. If I look there and we see that there is too much, the forecast for clouds is very bad, then we just close early and we go home to rest for save energy for the next night.
But using telescope time is so important that actually the Q coordinator is in call the entire night. So if anything happened during the night that is outside the specific that were provided, like say one instrument goes offline for any reason, the Q coordinator is on call, and James or Carlene will go into call and say, hey, GMOS is gone. Can you do something for us? And that person without coffee should go on his laptop and create a new plan that doesn't remove every single GMOS observation and be able to observe them. So it doesn't happen all the time.
Until midnight, but then after that we don't wake up the Q coordinator. We do that ourselves. got some training. I was skill coordinator before, for example, and also James, he was also skill coordinator. So if we get this kind of problem, then we do that ourselves. We change the plan.
Well, one can improvise to a certain extent. The software automates it to a certain extent, and so it makes it easier to pick things out. But it depends a bit on the key coordinator is much more familiar with what's available to observe than I am, for example, at the moment, just observing occasionally. So we go with what they recommend by default.
Yeah, I had to follow the Q coordinates sometimes, for example, for a target of opportunity or something that happened the last time, and it was early on the night. Then we called them, but much later, no, because then they also need to rest to work for next night plans.
So there's basically about 100 people all working to, keep us going here while we're doing this at night to, maintain the telescope and the instruments and plan things and check data and all kinds of stuff, run the offices, what have you, so that but it's all, down to us now to get it right so we don't waste their time.
Yes.
Yeah.
Yes.
Our job during the day is to make it as easy as possible for you at night we want you thinking as little as possible. That's our job during the day, right?
Yeah, during the day I go home, I sleep, and I do my stuff. I don't worry about the night, and then there is somebody doing that, and there is also a team of engineers that they go up there in the mountain during the day to check everything is fine. So we during the day we do nothing, and our work starts with the sunset. And then during the night we follow the plan. If we cannot follow the plan, we change plans. And if the plans cannot be done, we also do some planning as well in a small station. And the most difficult part, I think, of the decision making, especially when the weather is changing a lot.
Yeah, when multiple things go wrong at once, you have to change plans. You can't do the target you're expecting to do for backup, and you pick a different one, and suddenly it's a complicated setup that you weren't ready for. That's when it's hardest. Sometimes you have to, study a finding chart and figure out where the target is on the sky so that you can identify it quickly, or you have to change, configure the angle of the slit so that you get all the light in it. Sometimes those things take a few minutes of setup beforehand, so if you have to change programs suddenly because of the weather conditions, it can lose a little bit of time. Like Carlene says, you have to stay calm and do it quickly, but not too quickly.
Thank you so much, Carlene and James, for allowing us to shadow. Yeah, it was a fun session.
Thank you.
Thank you.
Thanks,
Good luck up there.
Yeah.
Thank you.
Thank you.
Cheers, guys.
All right.
Bye,
Aloha.
all.
Bye, everybody.